Alright guys, in this lesson we will discuss about transcendental functions. These are functions that are not power functions. So any function that is not a power function is a transcendental function, such as log function. A log function that is not a power function, so it is a transcendental function. Exponential function, that's a transcendental function. Trig functions are transcendental function. So any function that is not a power function is a transcendental function. So we did some of these, but we want to get deeper into how we find their antiderivatives. We know how to find their derivative, so we're going to review that, and then we will also discuss about how to find their antiderivative using u-substitution, especially when there are a product of two functions or a quotient of two functions. So first of all, remember that the derivative of ln is 1 over x. The derivative of e to the x is e to the x. That's a special function whose derivative is itself. Now this is a general exponential function. Its derivative it acts kind of like e to the x, but the only difference is that its derivative is a to the x, but the only difference is that you also multiply it by ln of base a, and that's the only difference between that and the e to the x. Okay, they're both exponential, but if it's any base besides e, then you also multiply it by ln of that base. The derivative of tangent inverse is 1 over 1 plus x squared. Another way to write tangent inverse is sometimes you might see it written as arctan. That's also tangent inverse. The derivative of sine inverse is 1 over the square root of 1 minus x squared. And again, sometimes you might see sine inverse written as arcsine instead of sine inverse, like the negative 1. Alright, so here is what we know so far. We know that the antiderivative of 1 over x is ln of x. Okay, and it makes sense because the derivative of ln of x is 1 over x. So the antiderivative of 1 over x is ln of x. There you go. We also know that the antiderivative of e to the x is e to the x. Now, whenever you have any other number in front of x, so in this case, notice that we have what? We have the antiderivative. We're trying to find the antiderivative of e to the ax plus b. Whenever there is any other number in addition to x, the antiderivative of that is itself, but then there's only one catch, and that catch is that you also divide it by the number in front of x, which in case is a, and then that plus c, you always add in that plus c, so that didn't change. Okay, now this is the general antiderivative for exponential function. We're no longer just working with base e. We could be working with any other base, such as 2, 10, 12, and so on and so forth. Now, to help us recognize what its antiderivative is, let's take a look at its derivative. So the derivative of a to the x, it's itself multiplied with ln of a. Okay, so the antiderivative of a to the x is also itself, but instead of multiplying, you divide. So divide by ln of a, and that's it. So keep this in mind. This is our first example. We're going to work with that problem. Now, because the derivative of tangent inverse is 1 over 1 plus x squared, therefore the antiderivative of tangent inverse is, the antiderivative of 1 over 1 plus x squared is tangent inverse. Now, this one is a little bit harder, and I want you to recognize the pattern, okay? Whenever you integrate 1 over a squared plus x squared, then it equals to tangent inverse of x over a, and then you also multiply it by or you divide it by a. So whatever a is, it also gets divided by a, and then you add in that plus c. That plus c always get added in. Okay, good. Now, because this is the derivative of sine inverse, therefore the antiderivative is sine inverse. The antiderivative of that is sine inverse. Okay? All right, another special one. Whenever you get the antiderivative of 1 over the square root of a squared minus x squared, that kind of resembles sine inverse, but the only difference is if this is a number other than 1, then you put a down there, and that's all you have to do. All right, very good. So let's take a look at how to find the antiderivatives of some of these transcendental functions. Okay, so here's our first example, the antiderivative of 4 to the x. That's a general exponential function. We're going to apply this rule to find the antiderivative. So here's what we know. So the antiderivative is, according to the rule, it equals to itself, and you multiply it by 1 over ln of whatever that base is. So in this case, the base is 4, and then we add in a plus c. All right, look what it says. See, itself 1 over ln of whatever that base is, and then plus c. Now, there are times when you will see that the answer will be written like this. So there you go. All right. Example number 2. This is also we're going to apply this rule to complete the next example. But here's the problem though. Instead of having an x, we have a negative x. So right off the bat, we cannot apply this rule yet. We need to somehow turn that into a positive variable. In order to accomplish that, we will now use u-substitution. So let u equal to negative x. That will imply that the derivative of u is equal to negative dx, negative 1 dx. So, in order for us to make a substitution, we will need to get rid of the negative in front of the dx, because the dx here did not have a negative. So now we are ready to make a substitution and integrate. I will now replace that with negative du. So that gets replaced with negative du. Okay? And then the negative x, it will now be replaced with u. Alright, so now I'm kind of back to my business. I can now apply this rule. A is 7. Okay? So here's what we get. When we find the antiderivative of an exponential function, it is itself, but the only catch is we multiply it by 1 over ln of whatever that base is. In this case is 7. Don't forget to bring the negative over though. Okay? And then add in a c. So in our last step, we will need to replace what u is, and u is negative x, so we take negative x and we plug in for u, and then we follow that with a plus c, and we're done. Okay, here is a third example on finding the antiderivative of a product of two functions. The only way to do this problem is to do it by u-sub, and you have to recognize the pattern because there is an inside function. So you notice that you see like an exponential function here, but it is not raised to the x. It's not raised to a variable. So somehow we need to take this integral and turn this integral into something that we know how to work with. U-sub is going to allow us to do that because by looking at this problem, I know that cosine is the derivative of sine. So I will need to make a substitution to find the antiderivative for this problem. So let u equals to sine. It means that du is cosine dx. So now I can go ahead and make a substitution. So this problem will now become cosine dx is du. 3 to the sine is the same as 3 to the u. Okay? Now, remember that rule that I star on the other side, which is this rule. So I took the third example and I boiled it down to just the antiderivative of an exponential function. So according to this rule, it says that its antiderivative is itself times by 1 over ln of base a. So whatever a is. So go over here and we're going to complete this problem. So it's just itself. See, it's itself. And then we multiply that by 1 over ln of whatever the base is. So the base is 3. And then we follow with a plus c. Now to finish off this problem, we will need to plug in what u is. So u is sine of x. So plug that in and we're done. So it should look like that. Okay? I just replace u with sine of x. Again, in order to complete this problem, you need to memorize this rule. But from now on, you should memorize all these rules. How do you do that? Well, each day you review 1 or 2 rules, and then by the end of the third or the fourth week, you would have memorized all these rules. And this is one of the last things we're doing before our AP calculus exam. All right, let's do the next example. Now, as you first glance at this example, it might look kind of hard, but let me break it down for you to show you how it's actually not too bad. So the fact that there's a 2 out, the 2 here means that I can actually pull it out in the front, because any constant can be pulled to the front. That should be a plus, and then this is x squared. Okay. Now by looking at this integral, so far it resembles this formula, because it can't be this formula, because if it did, it would have a 1 before the plus sign, but there isn't a 1 before the plus sign. Before the plus sign, it was 9, right? And 9 can be written as 3 squared, right? Good. So therefore, it resembles this formula, which means that the antiderivative is going to be something like this, all right? So what is it? Well, first of all, remember on the back side, this number is 9. This number is 9. This number is 9, which I'll flip it back for you in a few minutes. That number is 9, which means that a is 3. So when we find the antiderivative, it will be tangent. So tangent inverse of x over 3 times 1 over 3. Okay, so let me show you. Right, see? Now, if that's still unclear, maybe this will be a bit more clear. Like that. So your a is 3. Now, according to the formula, there's a fraction, so 1 over 3, so that 3 becomes a part of the fraction, and then tangent inverse, and now it's x over 3 over a, but a is 3, so it's over 3, and you insert a plus c. That's it, you're done. Okay. Oh, and don't forget, there was a 2 in the front. We need to bring that over. So bring that in, okay? Bring that over like that. So simplify it down to something like that. Awesome, very good. Okay, this problem. Now, perhaps before we start, why don't we look at our formula and see what this problem resembles. 1 plus 4x squared. So 1 plus 4x squared, 1 plus 4x squared. So it's not this because it had a 1 before the x squared. It's actually that. It's actually this, okay? Remember it was 1 plus 4x squared. So it's going to resemble this, but it doesn't look like it yet. So here's what we are going to do. The first thing we're going to do is we need to somehow turn this into something square, and that is definitely doable. 1 plus, turns out that is 2x squared, so we turn it into something square. See? Okay, so now we are ready to use this formula to complete the problem. Okay, now to complete this problem, the first thing we need to do is we need to make a u-sub so that we can get this in terms of just a variable square, because the formula contains just a variable square. There shouldn't be a number there. So we let u equal to 2x, du is equal to 2 dx. We have a dx, so we need to get rid of the 2, and that means that 1/2 du is equal to dx. Okay, so keep that on the side. These are the information that we need. Let's make a substitution. Substituting in terms of u, first of all, dx right here gets replaced with 1/2 du. So 1/2 du. And then the 2x is replaced with u, because that's what 2x is u, right? Now, if we look at just the integral 1 over 1 plus u squared, that is exactly the same as this. See? The only thing that's different is instead of using the letter x, we use the letter u. So its antiderivative is going to be tangent inverse of u for our problem. So let's write that down. So see, this is equal to tangent inverse of u plus c, and then we bring over the 1/2, and then finally we substitute what u is, which is 2x plus c, and we're done. Alright, so u-sub is kind of nice. It takes care of situations like these. It took care of situations like that, it took care of situations like that. But that's as hard of an integration as it gets. It doesn't get any harder than that in Calculus AB. Okay, good. So before you start, look at a problem and then see which formula it resembles. Okay, and this will come with practice. The more you practice, the better you will become at these working with these sort of problems. First, there's a radical in the denominator, so it will resemble this formula. So a squared minus x squared, okay, is the antiderivative is sine inverse of x over a plus c. So by looking at this, a, as you can see, 9 can be rewritten as 3 squared, so a is really 3. So let's do that. Let's rewrite this problem. And by the way, dx is written on top, but this is another way of writing this problem. Okay, so that's how you write that problem. This is a right here, guys. A equals to 3. Okay, it clearly resembles this formula. So the answer to this problem is sine inverse of x over 3 for our problem plus c. Okay, so it is sine inverse of x over 3 plus c. Okay, very good. Okay, 2 more problems. Find the integral of 1 over tangent inverse times 1 plus x squared. So these more complicated problems will involve u-sub to turn it into a nicer looking problem. It might take time, but when you finally get it, then it's going to click a lot better. But we need to make a substitution here. And maybe if I write the problem like this, you will see where the u-sub comes in. Okay, so if I wrote it like this, it will be more helpful because these two integrals are the same thing. I just wrote it a bit differently. Okay, so here's what u is, guys. This is u. I'm gonna let u equal to that. Okay, so let u equal to tangent inverse of x. Okay, now from now on, you need to know how to find the derivative of tangent inverse. Its derivative is 1 over 1 plus x squared dx. That is its derivative. So I will now change my variable. So I'm going to replace that for my dx. My dx gets replaced with that. So check this out. So I replace this whole thing. It's this whole thing. right? It's this whole thing. That whole thing gets replaced with du. So replace that with du. And then the highlighted portion, that is u. There you go. See? And everybody knows how to find the antiderivative of 1 over u. That is just ln of u plus c. And then the last thing you do is you replace what u is. And in this case, u is tangent inverse plus c, and you're done. All right, the last problem. Find the definite integral from 0 to 1 of dx over 1 plus x squared. So get used to seeing or knowing that whenever you see a dx, it means dx is out here. Okay, so from now on, you should know what the antiderivative of this is, because the derivative of tangent inverse is 1 over x squared. Its antiderivative is tangent inverse. So the antiderivative is tangent inverse. But anyways, so we're going to let big F represent the antiderivative of 1 over 1 plus x squared. So if we know what it is, evaluate it at 1, evaluate it at 0, subtract the 2, boom, that's how you find the answer. Okay? So let's first find the antiderivative. We know that that's tangent inverse of x. We evaluate the antiderivative at the upper bound. Okay, so what does this mean? It means what is the angle, because we're talking about an inverse function. So what is the angle that would give 1 as an output for tangent? And that angle is the angle pi over 4. Pi over 4 is the angle that would spit out 1. Okay. We now evaluate the antiderivative at 0. So what is the angle that spits out 0? And that angle is the angle 0. So now when we have those two values, we subtract them to find the value of our integral, and the value of our definite integral is pi over 4. Okay, so what do? We discuss about what are transcendental functions. Transcendental functions are functions that are not power functions. So, log, trigs, those are early transcendental functions. We know how to do that. We know how to do that. We kind of know how to do that. We talk about it, but maybe you haven't done enough to see how it's done. But hopefully today opens up a bit more, it makes things clearer for you. We haven't talked about this until today, how to find the antiderivative of a general exponential function. Pretty simple, is itself. Just multiply it by 1 over ln of its base. Okay, we also talk about the antiderivative of 1 over 1 plus x squared. That's tangent inverse, because the derivative of tangent inverse is 1 over 1 plus x squared, therefore the antiderivative is tangent inverse. We also discuss about what happened when that's not a 1. Well, if it's not a 1, hopefully it's a perfect square, such as 9, so that we can get a equals to 3. And therefore, if we know a equals to 3, then it's pretty similar to the first one. There is just some values that go there, and there's an a that goes there. Okay? We know that sine inverse, its derivative is 1 over radical 1 minus x squared. So the antiderivative of 1 over radical 1 minus x squared is sine inverse of x plus c. So what if there is a number instead of 1? If there is a number instead of 1, hopefully that number is a perfect square. If that's the case, then inside the parentheses of sine inverse, the square root of a squared goes down there, and we're done.